Welcome to everyone out there. We've got groups from about 25 different states around the nation, and so we are so happy to have all of you with us today. I really also want to welcome our featured speakers, Kim Willis sitting next to me, and Andrea and Charis, who are in the Lunar Lab. Also participating, although you can't see her, is Suzanne Foxworth, and she is helping to make sure we can see things in the Lunar Lab. Now, today is probably going to be our last webinar session for this calendar year, 2018, but do stay tuned for more webinars in 2019. Now, as we are going to get started here, before we get into our content, I really want to make sure you all are familiar with our speakers, who they are and what they do. So as we get into perhaps starting here, I'm going to see if I can, I have way too many windows open, if I can share a little bit of a career highlight as we have our folks introduce themselves. So I'm going to see if I can come here, and this will be a good sound test as well. I'm going to start in the Lunar Lab, and Suzanne, let's go over to Andrea so she can do a brief introduction, a little bit about who she is and what she does here.
So my name is Charis Krysher. I'm a lunar curation processor here in the Aries group. I haven't been here quite as long as Andrea has. Not so lucky, but I've been here for about 5 years. I have a bachelor's degree in aerospace engineering with some geology classes under my belt. And this is totally the best job in the world.
Awesome. Well, we're so glad to have you with us today as well, Charis. So you sounded loud and clear, and now we're actually going to go right next to me, and we should be able to hear Kim. Kim, can you introduce yourself for us?
Well, my name is Kim Willis, and I grew up in San Antonio and Texas City, Texas. I have a bachelor's and master's in physical science, concentration geology from University of Houston at Clear Lake. I also have a master's in secondary education with specialties in earth and physical sciences. I am the manager. Actually, I'm the manager over sample science, so that's over curation and over research. I began my career here December 19th, 1983. So if you do the quick math, I'm coming up on a 35-year anniversary.
Excellent. And so you can see that we have some longtime folks here who really love what they do. And we actually have quite a few of them from Texas. So it's really neat to have our Texas folks with us and our Texas folks on the line. And we're also really glad to have all of you with us on the line as well. I'm going to stop sharing here again. And what we really want to do before we go into the virtual tour of the Lunar Lab is we want to make sure we set a little bit of context about the Apollo missions to the moon and how we got these samples that are here at the NASA Johnson Space Center. So Kim's going to lead us off. And Suzanne, I'm just going to mute you and hide your camera because we're going to pin Kim here so that we can make sure we're focusing on Kim before we bring people into the Lunar Lab. So Kim, let's learn about the Apollo missions, moon rocks, and a preview of the tour of the NASA Lunar Curation Lab.
So on the right, you heard from Andrea earlier, Andrea Mosie. She's the one holding the lunar sample. Notice that nobody actually holds it with gloves. You have Teflon gloves there. So that's what we call a basalt. And if you want to study geology, it's a vesicular basalt. On the left-hand side, you see astronaut John Young giving what he calls the high salute. So yes, we actually did go to the moon. We had 6 landings on the moon, as you can see here, and astronauts collected not just rocks, but also core samples, pebbles, sand, and dust. I put this in here because I grew up during this period of time. You know, landing on the moon was not a historical event for me so much as, you know, I lived it and I was there. So this was a very profound image looking over the moon with the astronauts. One of the astronauts described as magnificent desolation. As you can see, no air, no water, no nothing. It's a very interesting place, but it's also, geologically speaking, dead. Looking at the Earth on Earthrise, and you can see the stark contrast between the dark, in this case, moon, the dark brown moon, and then the blue and green and brown and beautiful Earth in the background. So they only see part of the slide. So this slide here shows that there were 6 landings on the moon by different astronauts, starting from left to right: Apollo 11, 12, 14. And on the bottom is, starting from the left, Apollo 15, 16, and 17. Notice that on the bottom that those astronauts had the lunar rover, and they were able to go farther and collect more lunar samples.
You can take your hour to go next.
Thank you. So I have a question for you. How many astronauts have walked on the surface of the moon, and explain how you came up with this answer? So please put your answers in the chat window.
So here's just our first question. We want to kind of get an idea of what you're thinking in terms of how many astronauts have walked on the moon. You just saw the slide of the crew from the different missions. So if you're coming up with a number, how are you getting that number? So I see some 12s, I see 18. She just showed 6 missions, 3 astronauts per mission. So if you're giving a number, we want to know how you're getting that. So KSE says 12, 2 from each mission. Murfreesboro says 18. Shaker Heights says 12 based on 6 missions that landed. Frank Long Elementary says 12. Some of them didn't walk on the moon, but they did go. Our solar system ambassador in Florida says 12 walked on the moon, 1 had to stay in the command module. North Hopkins says 6 missions times 3 folks. That's 18 that should have likely walked on the moon. Corpus Christi Catholic School says 18 because there were 3 astronauts per mission. Meadowwoods Middle says 12. Only 2 went down while the 3rd from each mission stayed in the command module. Leon Springs Elementary is mentioning 12 to 18 based on the 6 missions and 2 to 3 astronauts walking on the moon. Now, all answers should go in the chat. Q&A is only for you to ask questions. Randall Middles and a solar system ambassador says 12 men because some stayed in orbit on the moon. Well, this is fascinating, and one of the reasons we wanted to ask this. It makes sense. 18 folks went to the moon, but Kim, how many actually walked on the surface?
12 actually walked on the surface because most of you got it. 1 astronaut had to stay in the command module, which orbited the moon, while the 2 astronauts went down to walk on the moon. And so you can see in the slide here, on the left is the lunar module. This is before it descends to the surface of the moon. So in that lunar module, lunar excursion module, the LIM, there were only 2 astronauts inside. On the right-hand side, you see what the lunar module looks like after it has landed on the moon and comes back to the command module. Notice that the descent stage, the pads that you see, they're gone because they leave that part on the moon. So those are some really good answers. I totally understand why some people would think it was 18.
Absolutely.
Yeah, you know, 6 missions, 11 or 3 astronauts per mission, you know, makes perfect sense. But it was actually 12. There were only 2 of the 3 that went to the surface. Really good answers, really, and I can tell you really thought this out. And I just put this in here. It's a really cool picture, Apollo 11. This is astronaut Edwin Aldrin, or Buzz Aldrin, and he is stepping off the lunar module and onto the surface. And by the way, Andrea Mosie's actually met him, but just saying. So the rocks that came back from the moon, a lot of people think they were brought to this building, as Paige said, building 31, where we're sitting now, but that is not the case. It was brought to building 37, or the Lunar Receiving Lab, the LRL. And so you can see there are like 3 different levels to it. That was because when the rocks first came back, they were afraid, scientists were afraid that those samples from the moon could contaminate us. And so, as you can see, the very top of that building right there was like the highest containment for the samples. Then the second level was not as high a containment. And then that 3rd level you see is just for offices and stuff. So the moon rocks that you're going to see here On the left-hand side, they came in to the bottom. You can see them in a white, what we call isopod box. On the right-hand side are the glove boxes that were in the lunar receiving lab. Now, these glove boxes are different than the ones you're going to see today because the ones back then had a vacuum. That means there wasn't any air, there wasn't any nitrogen, there wasn't anything in there. They wanted to mimic what the atmosphere or what it was like on the surface of the moon, which again makes perfect sense, right? But the problem is that they had a really hard time containing or keeping that vacuum in those cabinets. So by the time they built the next building that I'll show you in a minute, they changed, and I'll explain that a little bit. So you remember the big white box? Well, inside that big white box were these metal boxes here, and you can see these are the rocks. It's the first time they opened it. These are the rocks that were inside the boxes. I put this in here because you can see there are different kinds of rocks on the moon. Again, this is a basalt, or like a volcanic rock. Again, you can see the vugs or the holes that are in there from the gas escaping. This is also another kind of rock called an impact breccia. So it's a rock made up of other rocks. You can see this type of clast or rock is different from the matrix or from these other kind. So basically two kinds, very basic grouping would be basalts and impact breccias. And on the left, I put this in here for fun just to let you know that some of these rocks can be very dusty, and this dust gets over everything. And this was the only time when you first brought them back where you could have all this dust and not really have to worry about recovering absolutely every bit of it. Because now when you work in the lab and you open up a rock that looks like that, you have to return all of it. Why? Well, because we haven't been back to the moon in almost 50 years. So we need to be careful with what we have. This is the building today where the lunar samples are kept. Now, a little fun fact is this little piece right down here, that is the base of the building. They put that there because, of course, in Houston, we have this ability or this possibility to flood. And so they built it half a floor higher than the other buildings. So this is the bottom of the first building, first floor. But on the second floor, which is where you're going to see in this virtual tour, that's where the Pristine Sample Lab, PSL, and the Pristine Sample Vault, two places you're going to get to visit, that's where they're housed up here in the upper floors of the building. And I want you to note, this is what, think about the slide I showed previously about in the Lunar Receiving Lab and how these cabinets look different. But I want you to note that on your virtual tour today, these cabinets are going to look even a little more different than what you're going to see. So take note of that and be watching for that difference. And this is Andrea. She's in the Pristine Sample Vault. This is, notice that in the Lunar Receiving Lab, in the vacuum, that the gloves were flat. They weren't, there was no pressure inside, but now we have nitrogen inside these cabinets and the gloves are out. Notice these are the bins. These are where the samples are stored. And again, you might note the differences in the type of cabinets that you see here. And finally, another thing I'd like you to note as you go on your virtual tour of the Lunar Lab, again, these are the different kinds of rocks, but ask yourself, how do you tell one rock from the next? Because we have 382 kilograms total of return samples. How do you tell them apart? Well, it has to do with what we call the generic or the sample number here. And then also note about these little cubes and these rulers that we put next to the samples, and be thinking about why we might do that.
Excellent. And so we're going to take you now that you have a sense that we had 6 missions to the moon, almost 2,200 samples that went to the moon, including rock soils and soil cores, and we have this positive pressure clean room. Now we want to take you into the clean room. So thank you, Kim, for sharing that bit of an overview of the Apollo missions. Suzanne, we want to take it over to you to be able to share the actual Lunar Lab itself. So,
okay, we're here in the Pristine Sample Lab. This is where we process the Apollo samples that came back from the missions that Kim just explained to you. It is a class 1000 clean room, which means 1000 or less particles of a size micron or greater per cubic meter. We are extremely clean here. That's why we have to wear these bunny suits and the hats and the gloves. But even despite us having to wear this and this lab being as clean as it is, we don't expose our samples to the open air. We only have them inside of these cabinets, which are nitrogen pressurized. They've only ever been exposed to either nitrogen or the vacuum on the moon. So that's why we consider them pristine. They have not been exposed to Earth's atmosphere. So Andrea is going to take off some of these gloves so you can kind of see what these cabinets look like. Each of these cabinets is dedicated to a particular mission. We do not mix rocks from different missions inside the same cabinet. This particular cabinet is the Apollo 17 cabinet. And the reason that we don't mix rocks from different missions inside the same cabinet is we don't want to contaminate rocks that came from one particular area of the moon with rocks that came from another particular area of the moon. So Andrea's going to stick her hands in the cabinet so you can see what it's like. So despite us having all of these cleanliness procedures in place, we still cannot touch the rock with our bare hands or even with the gloves from the glove box. We have to, only 3 types of materials can come into contact with the rocks. That's stainless steel, aluminum, and Teflon. So if you're going to touch the rock, you have to use a tool. Typically we use tweezers. If the rock is too big to pick up with the tweezers, then we'll either use a Teflon glove that goes over these black gloves, or we will use a piece of foil, aluminum foil, to actually pick up the rocks. Ta-da! There's our beautiful piece of foil. And there are the special Teflon gloves that we would put over our black gloves in order to pick up the rocks if we had to. Okay. So, then you can see some of the other tools that we have in this cabinet are the balance. We have to weigh the rocks before we start processing them, and then we weigh the rocks after we finish processing them to make sure that we have accounted for all of the total amount of the rock that we started with. Before we actually weigh the rock, though, we have to make sure that the balance has been calibrated correctly. So we have these weights that we put on the balance beforehand, and then we check that weight against the calibration weight and make sure that they are within tolerance. If they aren't, then we stop what we're doing and we get the balance fixed. I wonder how many students have used the balance in class. Go ahead.
For the groups out there, we were just wondering, give a little raise hand if you use a balance in any of the classes that you teach. So raise your hand if your students use a balance in any of the work that they might do in your science classes or other classes. So we're getting a good majority of virtual hands being raised. It looks like we have at least a good portion, and they're coming in, those raised hands. So that balance scale that you might be using in your school, this is a very important thing, as Cherie has mentioned, for actually working with the moon rocks as well. So it looks like the large majority of them.
We actually use a hammer and chisel to break the sample. And this is an example of the hammer that we use. Coming through.
And we also use a chisel. We have to sweep the floor of the cabinet between each rock. So you can see on this flow brush that we actually have lunar dust. And in this container would be all the small particles that we sweep up in between the sample. So all the tools in this cabinet are they're specially cleaned, they're double bagged, and on the outside of our cabinet door, we cut off one of those bags, put them into our air chamber, purge for 5 minutes before opening the inner airlock door. Right. That's our inner airlock door. Once we open that, after purging that air chamber for 5 minutes, then we pull all the tools in, and that's the same process for bringing in the samples. We're going to walk over to another cabinet that we call our display cabinet and look at the samples.
Now we're going over to the display cabinet.
So,
In this
in
cabinet,
this cabinet,
we
we
have
have 5 different samples. As stated before by Kim, we don't mix missions, but in this cabinet, because it's on display for our visitors, we have different missions in here, but we don't process them in here. So, from the information that Kim gave you, looking at the rocks that you see in the cabinet, and you can see numbers in front of the rocks. Our numbering system is 5 digits, a code 12, 14, and 15 begin with those numbers. A code 16 and 17, we drop the 1, and it begins with a 6 or 7. So you can tell the mission from looking at the number. Now, can you tell me what kind of rock that you're looking at by the description that Kim gave you?
So, so Suzanne, if you want to focus on one of those rocks, that 15016. So we're looking, so 15016, 0. So this is a parent rock. Can anyone identify? And Kim mentioned the type of rock this is during her presentation, but we'll see if anyone else can identify it. So Roaming Middle School says basalt. Shaker Heights says basalt. North Hopkins says a volcanic basalt. Leon Springs also says a basalt. KSC mentions a basalt. Lynn Haven says it's a basalt. Carlisle ISD, igneous volcanic basalt, as does Randall Middle, Smith Elementary, Harrison Intermediate School. They're all mentioning basalt, as does Frank Long Elementary. So basalts are volcanic rocks, and they have identified, I'm assuming, Andrea, the correct type of rock?
Absolutely. And this rock has a special name. It's called seatbelt rock. There's a story that goes with that. And for the Apollo 15 mission, once the astronaut had gone out as far as they could go in the rover, can you hear me?
We're having a little bit of trouble hearing Andrea.
Okay, tell the story, Charis.
Okay. So this is named Seatbelt Rock. Apollo 15 was the first mission where they had the rover on it, but they were only allowed to travel as far as they could with their oxygen reserves. They couldn't go any further than they could walk back. So they were on their way back at the end of the EVA, and the commander, Dave Scott, saw this rock sitting by the track, and he thought this would be a great sample to bring back. So he radioed down to Houston and asked for permission to stop and pick up this rock. However, NCC said, no, you're at the end of your reserve, you have to get back. So he told them, I'm having a trouble with my seatbelt. I'm going to stop and fix it. Well, that's a safety issue. So he was given permission to stop and fix his seatbelt, but no more of that geology stuff. So he stopped, he picked up this rock, he photographed it, he bagged it, he put it back on the rover, and the entire time his partner is waxing philosophical about the lunar landscape and how wonderful it is to be on the moon, and just basically wasting time until Dave got back on the rover and said his seatbelt fixed, and they went on about their business and finished up the mission. When they brought the rocks back, there was this extra rock sitting there that the folks on the ground had no idea where they came from, and they asked him where this rock came from, and he told them, oh, that's a funny story. And that's how it got named Seatbelt Rock.
Absolutely.
So can they identify any other kinds of rock? What about 60015?
Now, this might be tough to identify because they only actually heard about 2 different types of rocks. We never had a chance to go over the 3 different classifications. So they probably would know it's not a basalt, but they may not know of any other terminology to mention what this might be.
Any guesses?
So any guesses out there? We have from one individual who is saying that this might be an anorthosite.
Very good.
Awesome.
That's exactly what it is. And it dates back to the old days.
Others are mentioning feldspar, the possibility of a sedimentary rock. Lynn Haven is mentioning maybe a sedimentary. Smith Elementary is like, we really have no idea. But anorthosite, sedimentary, and feldspar seem to be coming up.
Okay.
Great. It is an anorthosite, and it has a glass coating on it. So the 3 types of rocks are breccia, basalt, and anorthosite.
What did you want to say about that one? Okay. So the one that you see on your screen right now is an example of Apollo 17 rock. It's the Children of the World rock. So this was the rock that was picked up by Jack Schmitt, who was the only geologist to go to the moon. And when he picked it up, he dedicated it to the children of the world. And a piece of this rock got sent to every country in existence at the time, the Nixon administration, and all 50 states as a goodwill gesture by the United States. So it didn't matter what the political climate was or what the relationship was between the U.S. And the Soviet Union or China or Cuba at the time, they all got a piece of this rock. And here's another rock, Apollo 16 rock, which we call Big Willis. It was the largest sample brought back from the moon, almost 20 pounds.
It had a nice white anorthosite cap on the top of it. And the little cubes that you see, NT, SBW, north, south, east, west, top, and bottom.
Okay. Tell them what. Okay, Kim mentioned this earlier, the cube, the orientation cube. Most of the rocks that were brought back from the moon had an orientation, and we keep that orientation here in the lab. So when we're beginning to process a rock, the first thing that we do after we weigh it is we orient it. And we take pictures of each of the sides. And then we make a cutting plan or a chipping plan where we say we're going to hit the rock in a certain place, and we think it's going to break in a certain way. And then we hit it, and it never does that. But now we've created new samples. So each of those new samples has an orientation. And so we now take pictures of that new sample in all of its different orientations and we keep those orientations down throughout the whole processing history of the rock. So when a scientist comes to us and says, hey, there was this analysis done on this particular piece of rock 20 years ago, we may not have that rock anymore. It may have been consumed already. It may have no longer exist, but we can go back to our records and maybe pick another sample that was adjacent to that original sample, and we can give that to them and tell them exactly where that rock came from and what orientation it is, and so that they can continue to do their analysis.
To the next rock.
And there's
Also
an Apollo 15
sample that's a regular breccia.
Okay. So a breccia is a sedimentary
rock that is made up of other pieces of rock.
This is a great example because you can really clearly see the different clasts, the very light colored clasts that are embedded in this, what we call a dark matrix. And we love these samples because you get pieces of the moon from all over the surface of the moon, not just the area where you pick up this rock. But this type of rock can give you a good understanding of what was going on all across the moon. So the rock that you were just talking about,
We will show them how we process. This is a data pack, and the data pack tells the history of the samples. So I'm going to go to one specific, the sample that we were just looking at.
can't hear? I can.
Can you hear me?
It's a little echoey.
Okay, then
Charis could talk about
it as well. The data pack is 15459, and that's the breccia that you were just looking at. And this is our process. The first thing we do, we weigh the sample. You saw our balance. Weigh the sample, subtract that weight from our database weight. It has to be within the balance tolerance. Then we began taking photo documentation.
And then here's an example of that cutting plan that I talked about earlier. So here you can see this is where they planned on cutting it. And then they begin to cut. And you can already see we're losing pieces. So they stop, take a picture, document where that piece came from, and give it a new sample number. And as they continue to cut, we're losing more and more samples. And eventually, the whole thing is going to crumble. And then finally, what we have to do is put the whole thing back together like a puzzle. So now we know exactly where each piece came from, and each of these pieces has a new sample number and a new orientation. And then each of these pieces gets weighed and photographed. And at the end, we have to add up the mass of all of those samples, and it better add up to what we started out with, or we go hunting for the piece that we're missing in the cabinet. But I also want to show you how detailed we are. We also gather up the fines and the chips, and they get their own sample numbers. So we can tell you exactly what happened to every gram that has come back from the moon. We started with a little less than 2,200 samples total brought back across all the Apollo missions. We now have over 150,000 samples just because we've broken the rock so many times.
Okay, we're going to come back here to another rock.
Apollo 15 sample, and it's called the Genesis rock. It dates back to the oldest age on the moon. So this one was picked up on Apollo 15, also by Dave Scott of the seatbelt rock fame. And this was the rock that really catapulted the large impact, the giant impact theory of the moon, the formation of the moon, to the most likely way that the moon formed. So at the time of the beginning of the Apollo mission, there were several theories that existed on how the moon would have formed, including one that said the fission theory, which said that a really hot, young, rapidly spinning Earth just randomly spun off a piece of itself that formed the moon. There was also the capture theory, which said that the moon formed somewhere else in the solar system and was captured by the gravitational pull of the Earth. And then there was this really odd, not very popular theory hanging out there called the giant impact theory that said a body about the size of Mars came along very early in the Earth's history and dealt it a glancing blow. It vaporized the impacting body and it blasted a bunch of material from the Earth into orbit, and eventually that material coalesced to form the moon. So during Apollo 11 and 12, what the scientists were finding was they were finding these sort of chunks of this white rock called anorthosite, which really intrigued them because the formation of a anorthosite is the conditions that have to exist to form it are you have to have a huge amount of energy, and you have to have a huge amount of magma that cools over a very, very slow period. And the giant impact theory actually provides those conditions. So in the case of the giant impact, you would have had a large amount of energy that released. The moon would have been covered in an ocean of magma that would have cooled over millions and millions of years. And that would have allowed this anorthosite, this white rock, which is made up of one mineral called plagioclase, which is, by the way, feldspar. So whoever guessed that feldspar was what made up anorthosite is correct. And then that would have floated to the surface, and eventually the entire surface of the moon would have been covered in this white rock. So by the time Apollo 14 and 15 came along, they were telling the Apollo astronauts to find a white rock. And they finally found it on Apollo 15, and that really clinched and answered the question of how did the moon form? It formed as a result of a giant impact. You look into this cabinet, we have two soil samples from the Apollo 11 mission.
One you see has been sieved, it's very fine, and the other one is a little more coarse grain. You can just say what the numbers are and stuff.
Okay.
Okay, and the number that, okay, the number that was given to the first one is 10084, and the next one is 10085. And what the astronauts did were, with Apollo 11, once they got ready to return from the moon and they had a rock box that was with a few samples, they just took whatever soil was right around the lunar module and put it in this box. So this is some of the soil that was actually just dumped into the rock box. It has proved to be very useful, but it was just dumped in there just as a filler to fill that box. So not to prolong time, and we do want to go into the vault, we're going to leave this area and we're going to walk to the vault area.
And I have to tell you folks out there, what you're seeing is something that people just rarely get a chance to see. Going into this lab with Andrea, Charis, and Suzanne, and now heading towards the vault, we've never taken a group towards the vault. So this is special.
Okay, right now we're in the pristine sample quarter. And this is the way that we transfer samples from the vault to the cabinets. So you're looking at the airlock chamber, and the samples will be in a hard container, and you'll see that once we go into the vault, and they will be in 2 Teflon bags. We cut off a bag out here in the quarter. We cut off a bag, and we put another glove on top of this before we open the door and put our hand in it. The glove that you see that I'm wearing is never put inside of this airlock. We always have another glove or a Teflon glove on. So we're gonna go back here, passing by the same Apollo 15 cabinet that you saw the Genesis rock in. And Charis will be opening our vault. You'll see some of the tools up here that we use in our cabinet. And Charis is at our vault door. She's already opened it.
It's heavy.
And she body pumps. So we're going to go into the pristine sample vault. And of course, again, you see nitrogen cabinets, and they are also by mission. These 2 are Apollo 16, the 2 right behind that, Apollo 17, and these cabinets are double cabinets because there is a tray in the front and the back. Okay, I went away. Okay, you have to talk.
Oh, it's my turn. Okay.
I went away.
Yeah. These cabinets is.
We can't hear me.
It's.
Oh, are we all cutting
Yeah.
off?
I hear you both loud and clear.
Oh, you can hear. Okay, all right. Well, right now, this is the Apollo 15 cabinet. And I am going to go into the gloves, open one of the trays, and that tray is already unsealed. If you notice,
All of these trays
we have inventoried every sample that's in those trays, and our database has been updated. So we can easily document where every sample is. So if you can look into this tray, you will see how the samples are packaged.
You would see how the samples are packaged. Wait, cut out.
That's Apollo 15 sample. And this is how some of the samples are packaged. Now these will have 3 bags on it, so that once I transfer it into this chamber to transfer it into a cabinet, then we would cut off the outer bag, and with a glove on top of the gloves that we wear, we would put it into the airlock. So looking at this sample, what do you think this is? You've seen them before.
So I don't know if you all can see through that bag. And again, we have never taken a group in and pulled out a sample like this. So this is really pretty special. And I think that North Hopkins, Randall's, NASA Solar System Ambassador from Brumby Elementary, KSC, and Corpus Christi Catholic School, they are all, Meadowwoods Middle School, they're becoming lunar geologists right before our minds here. And they're mentioning that that is a basalt. Now, as we're in this area, and you are absolutely right, even the Kalispel Language Survival School, we may have, because they're in the vault, the wireless capability there may not be, oops, I see that I'm gonna pin a different video. Okay, here we're back. And so are they correct, Andrea, in saying that this is a basalt?
Absolutely.
And that's beautiful.
Let's see, I think we have another one that they may, okay. And this is also Apollo 15 because we're in the 15 cabinet. Can you see this one?
So I don't know if you folks out there can notice anything about that. Now, Kalispell Language Survival School says a breccia, and as does Brumby Elementary and KSC. They're not 100% sure, but they're saying that's possibly a breccia.
But you see that white part, huh?
And North Hopkins says a high impact breccia. Now, what was that white rock that they mentioned, one of the oldest rocks? And I think they noticed that little bit of darkness as well as that white rock, which might have thrown them off. Now, Casper Planetarium's mentioning they think that's the anorthosite.
Exactly. This is an orthosite, but they're right with the dark part on there is glass, and it's the breccia. But that's the white part is an orthosite. Okay, so she's actually closing the vault door.
How heavy is that door?
18 tons.
18 tons. So you do the math. 18 tons. Now that's a heavy door.
And so this is the quarter, and it actually goes all around the lab so that every cabinet comes out to the quarter, which means that we never have samples opened or exposed out in the laboratory outside of those cabinets. They're always in the nitrogen environment. So Suzanne is just showing you some of the cabinets as she walks along. That's the Apollo 11 cabinet, our first mission that landed on the moon. And these are tools again. These are tools. If we're working in a cabinet, we just come out here and get a chisel. We have hammers. These are chisels, aluminum cups, tweezers. Here are our trays. We cannot set the rocks straight on the balances, so we set them on Teflon pads. But as I said before, everything is clean. We have a facility here, and everything is clean. These are different size and shape containers that we use, depending on the samples that we're working on. And all of them have a specific number. All of these are called number 9 containers. They have a different serial number scribed on all of them, but anything this size and shape is a number 9, 83s, 84s, 251s. All of them have different special numbers. That's right. And again, here's the cube with the north, south, east, west, and everything that will go into the cabinet will have to be clean. These are scoops. If we have a soil sample, then we use a scoop.
Are there any questions?
You know, I have a question before Murfreesboro is about to hop off. They were wondering, Charis, you mentioned about the sample and putting it back together in the data pack. How long did that take, they're wondering?
I don't know about that one. I can tell you from my own experience with a different sample, it can take anywhere just from 1 or 2 days to several weeks.
So that's quite a puzzle.
Yes.
Do you have anything to add?
It actually depends on the size of the sample and how many pieces it breaks into. So it's a very tedious process. And since they don't all break at perfect angles, if you're trying to get the surface of one to stand up, you may have to stick a little piece of foil underneath it or something to give you that orientation that you're trying to get, because they're not just going to fit back together just because they were broken that way. So you actually have to work at it. It is a tedious process.
And related to that, North Hopkins ISD is wondering, what's the main information you gain from the rock breakage? Why do you break rocks?
we have scientists, we call them PIs, principal investigators, all over the world who have grants to study and analyze a lunar sample. They're specifically looking for certain things. Some work with magnetics.
Water, they're looking for water in the sample. They're looking for the history of the Earth-Moon system, and beyond that, the solar system. All sorts of things. Yeah.
And so they actually put in a request to a group called CAPTIM, Curation and Analysis Planning Team for Extraterrestrial Materials. CAPTIM is a group of scientists, so they approve or deny. They recommend, actually, NASA headquarters does the final approval, but they recommend that the samples that they requested is either good for what they're trying to find out or not. But before we actually went to the moon, people didn't even realize that the age of the true age of the Earth. They thought the Earth was millions of years old. After we brought the samples back from the moon, then through the research and exploration, it was determined that the age of the moon was billions of years old. So that's one of the things that was learned from bringing the samples back from the moon.
So your customers are, because this is a question related to that from the Kennedy Space Center. So the customers for for the rocks that you break up, are they really mostly scientists? Are those your only customers, these principal investigators or scientists?
Yes, basically, yes, they are. We have samples that are different places that we send out, but most of them are on display. We have display samples that we send to museums and other places, but as far as receiving samples, they are scientists. They may have students, research students and interns or what have a postdoc students working along with them, but the samples are allocated to scientists at universities or official scientific institutions.
Excellent. Thank you for these answers, as these questions seem to relate to what you were talking about. Now, also related to that are those rocks in the vault. Some of them have never been investigated by a scientist or a principal investigator.
The ones that you see in the cabinets that we were pulling out, at least a piece of all those rocks have been. The rocks that are in there they have never gone out of the nitrogen environment or been sent out. They're all pristine, so they're still in this laboratory. But pieces of them were broken off, given a daughter number, a common number, sent out to an investigator. They did their study and analysis. If they return them to us, we have another vault like this for return sample processing. Those samples never come back to this laboratory or vault. So we have pristine sample processing, we have return sample processing. But the principal investigators who actually receive samples and return the samples, they have to give us a history of those samples so that if another PI wants to study or analyze the same sample, they'll know exactly what was done to that sample.
We do have 3 samples, core samples, that have never been opened since they came back from the moon. Those get opened.
And these students that are on the line with us today, they may become future lunar geologists, and perhaps they might want to study a sample that's never been totally investigated. So, you know, for these up and coming lunar geologists, are there benefits to some of these samples never having been worked on yet?
Absolutely, because what we're doing now, because technology is so much better, we have a process of CT scanning samples, so you could actually see what's in the middle of the sample. So we have samples that have not been broken up, but if we CT scan it and you use that scan, you may find something in the middle of this sample that was not even shown on the outside surface of it. So that's the importance of technology, new technology, and continuing to be innovative.
There's also another example of technology moving ahead is we found that these rocks actually contain a lot more water than they originally thought when they brought them back in the 70s and started doing the analysis. And we're talking about orders of magnitude. Now, we're still talking parts per billion, but still there's a lot more water that makes up the moon than we originally thought. And so that goes back to the original question of how the solar system formed. Where did this extra water come from? And that's one of the big questions that a lot of our principal investigators are trying to answer right now.
Because there was a point of time when I used to do a tour, I would say there's no water on the moon. Now we can't say that. We just say there's no free flowing water on the moon.
No free flowing water, but there actually is H2O locked up in those rocks and a lot more than we ever thought. And you know, that's so interesting because with, as you mentioned, the improved technology, the new technologies, and new scientists asking new questions, even though these rocks, you know, come from missions from the 60s and 70s, there's still so much to learn. Now, Corpus Christi Catholic School is wondering what would happen if the rocks were exposed to Earth's air?
Okay, since we have oxygen in the atmosphere, automatically, I mean, after sitting out in our atmosphere for a while, if there's metal in the rocks, then what happens if you have a nice shiny nail and you set it out in our weathering process? We know it's going to rust. That should have been a question that I was asking them. I should have. Well, the rocks will go through that same process. It's not going to happen immediately, but it's going to go through that same process. So that's going to change analysis. That's why we process in the nitrogen cabinets. It's an inert gas, and there are other gases they could have used, but this is the one that they selected. And all the scientists, PIs, know that that's what we use. So if they have any analysis and this is going to affect it, they know to factor that into their analysis.
And that documentation is so important with everything you mentioned.
Yes, it is.
So you all in school might think, oh, I have to take so many notes and write so much down. Well, with these lunar samples and the work that these two gals do, there is no shortage of note-taking and detail that gets written in. So it's so very important to document everything.
And another thing, our numbering system, I told you we had 5 digits. We have a sample number, which is 68815, but we also have 68115. It's very important not to transpose numbers because you're talking about 2 different rock numbers, same mission, but you're talking about different rock types. So it's very critical to what we do that we
Pay attention.
Pay attention.
Absolutely.
Do y'all have a favorite rock?
Very important. Now, here's a Kalispel Language Survival School is mentioning, and I don't know how much detail you might be able to answer, but what's the procedure to get gas from the rocks to calculate that the moon once had an atmosphere or that it has had an atmosphere? Can you do that through some research?
Yes, actually you can. Now, with the lunar samples, the moon has never had an atmosphere. So, you know, you're not going to get good research from that, from these samples. However, meteorites are a great sample to do that research on because they tend to come from, well, they come from other planets, right? They come from asteroids, which also don't have an atmosphere. They come from the moon, which doesn't have an atmosphere. But Mars has an atmosphere. So not great research to do on these rocks, but on other space rocks, yeah, you can do that. And there are actually several ways that you can do that.
And we don't actually do analysis here in our laboratory. We process the samples and send them out to others who actually, but we do have a group of scientists PIs in our building who actually do all kinds of analysis.
And some of that analysis certainly is quite technical, but as Charis
Yes,
mentioned earlier, that really important aspect of kind of coming to a consensus or a bigger consensus on the formation of the moon itself, these rocks have really, really helped to solidify that thought. Though there's still others that might disagree, but it's certainly that leading hypothesis because of these rocks.
Yes.
Now, interesting question from Casper Planetarium came in about the vault door. You said it was 18 tons. Why so heavy? That's the question.
Actually, that vault door is a Federal Reserve vault door. That's actually this vault is the kind of vault that the Federal Reserve would have. It was actually built because the lunar samples are priceless. You cannot put a monetary value on there. They are not for sale. They belong to you. They belong to the government. And so there's no monetary value that you could put on a lunar rock, but they need to be stored in a place that's like our Federal Reserve. And that's what this door is. At the time that this facility, and I know the Federal Reserve has a new, stronger vault door because I've gone to the new facility, but this at that particular time was top of the line in that area. But it's for the security. And everything we do here is a two-party system. When we transfer samples from the vault to the laboratory, it takes two people. So for verification of sample numbers and also for the security of the samples.
Awesome. And do you have a few more minutes to stay on the line with us?
About two.
About
a few.
So before we lose them, first of all, for the groups that are still on the line, I really want to take a moment to thank Charis and Andrea for sharing such a special place. I mean, this is the only place in the world here at the NASA Johnson Space Center where we curate NASA's extraterrestrial samples, including meteorites, moon rocks, solar wind particles. But for them to share this with all of you and their expertise, and we again apologize for the technical difficulties, but Andrea and Charis, you're amazing. And Andrea has been around for how many years, Andrea? Because we might have missed that.
43 years.
43 years. And Andrea is one of the most...
And I still love it.
And she still loves it. I heard that. And, you know, and that's the beauty of working in a place like this that we wanted to share with all of you. The excitement that we still all get every day we come to work. 43 years and counting. Charis hasn't been here that long, but we'll see in 40 years if she's still here. Her career is just beginning, but it's students out there that are going to be the new Charises and Andreas that are in the lab. And so we really do need you. We haven't collected a lot of moon rocks lately, but hopefully we'll get back there soon and collect more moon rocks. So I know I probably took up your 2 minutes, but I'm going to give you any last comments you have for our groups that might still be on the lines that you'd like to share with them.
Actually, to let you know that you can achieve anything that you put your mind to it. You need to set a goal and go for it. The thing that I look back on my life, I was in pre-med and I actually wanted to become a doctor. So I took all my science classes, chemistry and math. My last year of college, I changed my mind. I got my degree in chemistry and math, started working at NASA right out of college, and then I started working on my master's of physical science and geology because I did not have that background, but I knew what I was doing, so I knew I needed that background. So the education process continues constantly. Even working here all these years, we're still learning and growing. You know, you don't know it all and things change. So you learn with that. So I just tell you to do your best in what you're doing. Find your goal, go for it because you can achieve it.
Excellent. Thank you, Andrea. Charis, any last comments from you?
I just really want to echo what Andrea said. I started as an aerospace engineer over in operations, so I was working with the flight controllers, and I decided to go through a career change. So I did exactly what Andrea said. I didn't have the planetary science background, so I went back to school to get it. And I knew that this was here. I started to talk to people who worked here, and that gave me that path and those goals that I started to work towards so that eventually I could get here. So know your path, work towards it, and be willing to change.
And that's a great message, because you got to be willing to change and open up your horizons to new things that you never knew might inspire you.
And failure is not an option.
That's right. Failure is not an option. Just because you don't achieve one goal doesn't mean you have failed.
Absolutely, absolutely.
Absolutely. And thank you so much. I know your time is precious, and these two have to run off to do some additional things. So thank you, Andrea and Charis. Thank you, Suzanne, for getting us connected.
Thank you.
And for all of the folks that are on the line, thank you for spending some time with us today. And we hope you learned some things. We hope we maybe inspired you a little bit. And we hope to connect with you sometime again in 2019. So with that, we're going to bring this to officially to a close. Thank you, Andrea and Charis. We look forward to connecting with you soon.
Okay. Bye-bye.
Bye-bye, everyone.